will be working on. Outputs are going to be just a motor system, little gearing, running a load, and we have theta and omega are our outputs in the system. Okay. First step is we're going to get the state equations modeled. Okay. This one's fairly simple. If you remember the model for, I'm going to do this in the electrical side and the mechanical side. Motors have resistance and inductance. Current source, remember that one problem you have a current source, what's going to happen to the resistance and inductance in this? Yeah. So basically it just kind of drops out. Okay? So this really ends up being a torque source acting on an inertia. Of the motor, and we have the gear. So I have, let's say, theta of the motor, omega of the motor. We have this load, right? And this load, let's say, has some friction to it also. And this is our output. All right. So since this current source is on this thing, as you did that one homework problem, it can supply whatever voltage is needed. So if you really look at Kirchhoff's voltage law of this, it doesn't really give you any more information. It basically says that the applied torque is the torque constant times the input current. And then if you kind of look at a simple thing on this, sum of torques and motor. It's just a kind of brute force. You can all solve, even if you can't remember bond graphs, linear graphs, or anything, you can all solve things. Motor systems fairly simply this way. We have JF motor times the acceleration plus friction times velocity plus, let's say here, the torque going off to the gears is equal to the torque applied to KT by FT. With all the loads in this thing, I have, of course, inertia, inertia motor, friction of the motor, and then this gear is applying some torque on this motor back from the load. Make sense, everybody? What's the gears? Theta, omega, and torque of the motor. It's in that direction. And it's arbitrary which way I want to draw these things there. I think I drew them in opposite directions here. Theta, omega, T, the output. So basically, this is gear 1 with number of teeth in 1, gear 2, number of teeth in 2. And can't remember relationships, you can always work them out because what's matched for gears? At the teeth.
Velocity.
Can't be any slip. Tangential velocity has to be equal, and the static forces have to be equal. So M1 theta M is equal to N to theta, and it's that because the way I drew the arrows. All right. All right. And then same thing for the torques. because of the way I do the arrows, that's a minus sign in source. All right. Let's look at the load, the last part. And the load has J and some friction to it. And it's whatever torque from the gears is acting on it, J omega dot plus d omega. And combine all these things. So what I want to eliminate are these variables. So I substitute in for those in terms of theta. So everywhere I see a theta m, I'll put in an n2 over n1 theta. Every time I see a torque of the motor, I'll put in minus n1 n2 t. Combine everything together, and we get our differential equations. The motor, n2, n1 squared. You should expect to have a gear ratio squared showing up in these. Plus the inertia of the load. Not. Friction of the motor. N2 over N1 squared. Again, I'm going to that square. It shows up. Omega. N2 that's the differential equation, combining everything together. Well, this essentially is an equivalent of J. Leave it at that. This is an equivalent of friction. And let's combine all this part together. And let's just call that case of it. Right? That's a constant. Okay? That means I don't have to keep writing these things down. So it makes sense how to do this well. Pretty straightforward. Linear graph, bar graph, same thing. This is fairly simple one to do just as is. So we want to get this in state form. So we have the differential equation. Next one's going to be what? Our first state variable. What's it? You want omega or outputs or what? Yeah. Why not put in theta? That's going to be one of our primary outputs. Let's let it be theta. Okay. So x2, x1 dot versus omega, which is x2. X2 dots is equal to, well, omega dot, and I have that here. So it means I put everything else on the right-hand side, and I have my state equation, which will be minus B equivalent over J equivalent times omega, which is x2, plus this constant Ki over J equivalent times T, which is our input. Okay, so our state equation, matrix form. 0, 1, 0, 1, 0 minus B equivalent over J equivalent. Our state vector. And our input matrix, which is Ki over J equivalent. And our input, which is IP. ways. I could say it's theta and omega. We have two outputs, perfectly fine. Let's take it just one output for the moment. I'll say my main output is theta. Okay? Plus 0. Now, everybody see how we got the state equations? All right, so we have our model, first step. The next step.
What are we trying to do?
We're going to design a controller for it. I want to be able to control, really I'm trying to control theta. So what do I have to do before I can do anything else? Yeah, I can check stability. In fact, what would you know about stability in the system? Well, what are the eigenvalues for? Find the eigenvalues, it's a good thing. Do that. In some sense, I don't really care that the open loop system is stable or not, because I can only stabilize it. It's nice to know. So, how do I get the eigenvalues for this thing? The poles, the roots of the characteristic equation. All right, hopefully you've set that as a neural connection in your brain now.
Yes, I'm
What do you
sorry.
think that's what I say? And that's what. For this system, it's S minus 1, 0, S plus, say, B over J. That's what determinant of that. And I have S squared plus B over J. S. There's your characteristic equation. Roots of that are what?
0 and negative B.
0. And minus B over J. This one, that root is what, stable or unstable?
Stable.
Stable. That root,
Marginally stable.
marginally stable. Basically, it's a pull right at the origin. Yeah, it may not be exactly the best thing I want for this thing, but good step to do. But before we can do a controller, we need to check for what?
Controllability.
Controllability and observability. Let's do that. Okay, let's check controllability first. What is the controllability matrix for the system? Going to be the B matrix, which is 0, K, let's just call it K and J. Okay, next one.
KB.
It's A times B, which is, yeah, K over Ki, K over J, that one, and minus DK over J squared. Did I do that right? Correct or not correct? This is exactly the thing you'd be getting on test. Correct. Okay, what can you tell me about that? Is it full rank?
Yes.
Yeah, so full rank. To self-control. All right, let's check observability. This guy. first row or first column, depending on whether they do the transpose or not.
C.
C would be what? First row, right? So we'll put that as the first row under that. And then the second row will be what?
C.
C times A, right? So C times A, which is, thanks for breaking these things out. 1, 0, 0, 1, 0, 1. Okay. So this is 0, 1. Full rank? Better be
Yes.
identity matrix. Yeah, rank. 2. So we're observable. So now we're set. We can design a controller without any having to do minimal realization. All right. And we checked the Icon Valley say the original system's kind of marginally stable. And for those that 52, 6200, what system type is that for steady state error? Anybody spot it, what it is? Those that have that class, you won't know what I'm talking about. Type 1. Okay, so we're going to design a controller. So let's get some specifications of what this is to do. So let's specify design. I'd like to have no more than 5% overshoot. Transient response. What's that mean? What am I specifying here? Yes, the damper ratio. Okay. You might have to remember what that looks like. You have to calculate it. I have, what I want is inverted calculation of this thing. Data is minus natural log of our overshoot, which is 0.05. All over square root pi squared plus the natural log squared of 0.05. And that's equal to 0.69. So we have an inequality here. We want no more than 5% overshoot. So is the damping ratio 0.69 and bigger or 0.69 and smaller? Bigger. Bigger overshoot, less, bigger damping, less overshoot. So I'd like to have this thing greater than 0.69. Okay. All right. So we have our order system here. Set order. Right? Simple. So let's look at the desired, see what we know so far. The desired characteristic equation